Today we want to talk about complex numbers, specifically complex roots, because we need trigonometry to talk about complex roots of numbers. And if we're going to be solving equations, we're going to need to know our complex numbers. So let's get familiar with these complex numbers. There are certain things that we know. We know that the square root of 4 is 2. We know that this is not where the end of the story. We know that if we want to solve x squared is equal to 4, we can't just write the square root of 2. We know that there are two solutions, 2 and negative 2. Yikes. This is something that we were talking about last week. There's the solutions that we get just from the inverse, but the inverse is naturally limited. So the inverse of a square is a square root, but there's extra stuff that goes along with it because we might not have any real solutions. So if I ask you for the square root of negative 4, I didn't say that there were no solutions. We said this is not a real number. So when we talk about the square root of a negative number, we weren't trained to say no solutions. We were trained to say this is not a real number, or no real solutions. So if I ask you to solve the equation x squared equals negative 4, you would just say there are no real solutions. Instead of saying no solutions, we specify no real solutions. We even tie this concept to things like graphs. So if we look at the graph of x squared minus 4, we know we'll have a parabola. That was a terrible parabola. It needs to be thinner on the bottom. I don't know if you need to hear this, but a lot of times you might hear that a parabola is a U-shaped graph. It is definitely not a U-shaped graph. It's a rounded V. U's are vertical on the sides. U should be vertical on the sides. V have an angle to them. But parabolas are rounded, so it's a rounded V, not a U. See how the sides are kind of going off at an angle, not straight up and down. So the parabola x squared minus 4 has two x-intercepts, 2, 0, and negative 2, 0. So x squared minus 4 has two real solutions. And we can see them as the x-intercepts of the graph of the expression. Now, if we look at the function y equals x squared plus 4, we have the same shape, but now the parabola is going to be 4 units above the x-axis. So x squared plus 4 equals 0 has no real solutions. And we can see that there are no x-intercepts. Two real solutions, two x-intercepts. So, but x squared plus 4 has no real solutions, it does have complex solutions. So when we look at expressions like the square root of -4, we know that this is not a real number. The square root of -4 is not a real number. So if it's not real, then what is it? So we were dissatisfied with this not a real number business. This is not acceptable. So we made something up. What if the square root of -4 is not a real number, but some other kind of number? So we invented an imaginary unit. How do you spell imaginary? Is it an E-R-Y or an A-R-Y? One of these days I'm going to have to learn to spell this word. It's an A-R-Y. One of these days I'm going to remember that. But it is not this day. Y'all haven't been in my class before, but every time I have to write the word imaginary, I have to look it up. So we like I was there, invented this imaginary unit, the imaginary number. I is going to be the square root of -1. That is, I is not a real number. I is the number such that when you square it, you get -1. So this is called the imaginary unit, and we use I to represent it. So although the square root of -4 is not real, it is imaginary. So if we want the square root of -4, it's going to be the square root of 4 is 2, and the square root of -1 is I. If we want to solve the equation x squared plus 4 equals 0, we have two solutions, 2i and -2i. Any questions? So we may have seen this before. It's what we do when we have a negative under a radical. The square root of a negative is going to be an imaginary unit. It shows up first, usually when we're solving quadratic equations, because the quadratic formula involves a square root. And the square root of b squared minus 4ac might be imaginary. So that's where our imaginary units come from. Graphically, we know that if we have imaginary solutions to our quadratic equation, that means there are no x-intercepts. So if we're looking at a parabola with no x-intercepts, we know that whatever quadratic made that parabola will have complex zeros. So they'll involve I in some fashion. So now that we have two kinds of numbers, real and imaginary, we have to combine them. Complex numbers are a combination of real and imaginary numbers. Hey, I remembered. I know you're thinking, oh, of course you remember because you just looked that up like 5 minutes ago. I was like, well, 5 minutes is a long time when it comes to my memory. A complex number has the form a plus b I. A is called, where a and b are real numbers. Oops, I should say that. Where a and b are real numbers. A is called the real part. And B is called the imaginary part. So a complex number has these two parts to it, a real part and an imaginary part. We should note that real numbers are also complex numbers. They just have an imaginary part of 0. So real numbers are also complex numbers. Real numbers are also complex numbers. We can write the real number 5 as 5 plus 0i. So real numbers are a subset of complex numbers. So real numbers are a subset of complex numbers, just like imaginary numbers. And then inside the real numbers, we have our rational numbers and all our other subsets. So you've probably seen a picture like this before. So we're just expanding the real numbers to include imaginary numbers, putting those together and calling it the complex numbers. So real numbers, the real numbers are a subset of the complex numbers. Other than that, they kind of behave just like we would expect anything else to behave. So for example, if I have to add a couple of real numbers like 3 plus 2i, if I want to take this complex number and add it to the complex number -5 plus I, 3 minus 5 is -2, and 2i plus I is plus 3i. We add complex numbers, we get a complex number. We can subtract complex numbers. This requires our polynomial skills. But since our polynomial skills are just number skills, we know how to deal with that. 3 minus a -5, that's 3 plus 5, 8. And 2 minus I is plus 1i. We can even multiply complex numbers. This is just requiring our polynomial skills. If I have 3 plus 2i, and I want to multiply by -5 plus I, then we just multiply each term in one polynomial by every term in the other polynomial. 3 times -5 is -15. 3 times I is plus 3i. 2i times -5 is -10i. 2i times I is plus 2i squared. A couple of extra things can happen here. We have like terms as plus 3i and minus 10i are like terms. So I can make that minus 7i. I'll go to minus 15. The other thing that can happen is that I squared, since I is the imaginary unit, I squared is equal to -1. So plus 2i squared is the same as minus 2. Then we end up with some like terms again. Now I can combine the -15 and the negative 2. Negative 15 minus 2 is negative 17, and I still have minus 7i. So it's just polynomial operations, but with complex numbers. We can even raise complex numbers to exponents. So if I have minus 5 plus I squared, I can just write 2 copies of minus 5 plus I and multiply them. So I get 25 minus 5i minus another 5i plus I squared. I can do the same things that we did before. Minus 5i and minus 5i is going to be a minus 10i because they're like terms. And I squared is equal to negative 1. 25 minus 1 is 24. Shouldn't have been so stumped by that, but you know, it's early. So we're not doing anything new. This is just how numbers work. They just happen to be complex numbers. The complex numbers are looking like polynomials, so we just use our polynomial strategies to deal with these. So we want to add some stuff to your knowledge base about solving polynomial equations. So let's talk about some things about polynomials that you may or may not have heard. Actually, let's go about this a different way. So there are things other than square roots. We know cube roots. So we know that the cube root of 8 is equal to 2. Because 2 times 2 times 2 is equal to 8. So the cube root of 8 is 2, since 2 cubed is equal to 8. When we think of 8 to the cube root of 8, we think of that as 8 to the 1/3 power. And so the inverse of a cube root is a 1/3 power. So the inverse is a third power. Is putting things together with our discussion about inverse operations in reverse order. A cube root is a 1/3 power. And the inverse of an exponent is a reciprocal n exponent. So if I ask you to solve the equation x cubed equals 8, the implication is that I just want the real solutions if I'm just going to take 2 as the answer. So for example, if I said solve x cubed equals 8, we say x equals 2. And we stop there. This is the only real solution. With odd exponents, we always get one real solution. With odd exponents, we get one real solution. An odd exponent polynomial equation will give us one real solution. I had to write something in orange and red because I have red and orange pens in play today. And the red was looking really orange. And so I had to bring out the orange pen. Now they definitely look different. Because what we see is not always what we see. If I'm not looking at the orange, all of a sudden the 2 to the third equals 8 looks really orange. Now it looks more red. I don't know. We know that when we have a polynomial equation with an even exponent, we could get 0 or 2 real solutions. So if I say, we know that the fourth root of 16 is also equal to 2, since 2 to the fourth is equal to 16. If I ask you to solve x to the fourth is equal to 2, or sorry, x to the fourth is equal to 16, we know that there are 2 real solutions, x equals 2 and -2. But if I ask you to solve x to the fourth equals -16, there are no real solutions. Even exponent polynomial equations will have 2 or 0 real solutions. Notice that 2 and -2 are real solutions to x to the fourth equals 16. Because 2 to the fourth is 16 and -2 to the fourth is equal to 16. So these both work. If I take 2 to the fourth, that's 16, and -2 to the fourth is also 16. So that's just background for where I want to get with these polynomial equations. Any questions? Thought of setup in this one. All right. So let's look at powers of I. When we raise I to a power, there's only 4 things that we can get. We know that I is the square root of -1. And we know that I squared is equal to -1. So what this means is if we want to calculate I cubed just means I squared times I. I squared is -1, so I cubed is -I. If we have I to the fourth, I can think of I to the fourth as I squared times I squared. Since I squared is -1, -1 times -1 is +1. Now here's where the pattern starts to repeat. This is something that we as trig students are going to be looking for. We see this I squared, I cubed, I to the fourth. We get I, -1, -I, +1. If we take I to the fifth, that's just an I to the fourth times an I. And I to the fourth is equal to 1. So we're back at the start. I to the sixth is an I to the fourth times an I squared. I to the fourth is 1. I squared is negative 1. I to the sixth is negative 1. I to the seventh, you can see where this, maybe you can see where this is going. I to the seventh is I to the fourth times I to the third. I to the fourth is 1. I to the third is negative I. So I to the seventh is negative I. I to the eighth, we're back to 1 again. I to the eighth is like an I to the fourth times an I to the fourth. I to the fourth is 1, and 1 times 1 is 1. So when we look at powers of I, there are 4 things that we can get. I, negative 1, negative I, and 1. Here we have I to the first. Oops, I spelled first wrong. I to the first, I to the fifth, I to the ninth, and so on. Negative 1 will be like I squared, I to the sixth, I to the 10th, and so on. And they're just all off by 4. Because every time we have 4 powers of I, a fourth power of I, we just have 1. Negative I will be starting with I cubed, I to the 7th, I to the 11th, and so on. And I will be all the powers of 4. Sorry, all the multiples of 4 power of I. So I to the 4th, I to the 8th, I to the 12th, and so on. All right, so what we should notice about powers of I, when they show up as complex numbers, whenever we raise a complex number to a power, we're just going to get a polynomial in I, and a polynomial with in terms of I is always just going to come down to a complex number, because all the powers of I are just either plus or minus 1 or plus or minus I. So for example, if we got a big complex number, if we do some stuff and we get, let's say, 7 plus 5I minus 4I squared plus 3I cubed minus I to the 4th, I can replace all these powers of I with either plus or minus 1 or plus or minus I. So this is equal to 7 plus 5I minus 4I squared. Since I squared is negative 1, this is actually going to be written as plus 4. And now it's like term with the 7. I to the third is negative I. So I can replace the I to the third with a minus I. And I to the fourth is equal to 1. So I'll replace minus I to the fourth with minus 1. So now I have a bunch of like terms. I've got the 7 and 4 and negative 1. So I get 10. And then we've got plus 5I and minus 3I plus 2I. So even though we're doing polynomial operations on these complex numbers, it'll always break down to just some complex number. So what we're going to talk about on Wednesday, since we're out of time today, is the following. X to the n equals some constant has n complex solutions, counting multiplicities. We're building up to the fundamental theorem of algebra, which seems a crazy thing to do in trig class, but we don't get to talk about the fundamental theorem of algebra pretty much until we're out of algebra. We just have to, even though it seems like it should be backwards. Shouldn't we open with the fundamental theorem of algebra? But no, that's not how we do it. It's like building a matrix with utopia. We just reject it. It never worked. I mean, it wouldn't work. I'll have to edit that out. So we focus a lot on the real solutions. X to the third equals 8 has one real solution. X to the fourth equals 16 has two real solutions. X to the fourth equals negative 16 has no real solutions. But there are complex solutions. X to the third equals 8 has one real solution, but it has three complex solutions. X to the fourth equals 16 has only two real solutions, but it has four complex solutions. If we start allowing complex numbers in the solving equations game, then our polynomials, whatever the degree is, that's how many solutions we're going to have, counting multiplicities. All right, so that's the next big thing for Wednesday. Even though this is trig class, we got to talk about the fundamental theorem of algebra. All right, that's going to do it for today. I'll see y'all on Wednesday. Everybody have a good couple of days, and thanks for playing.